Good morning. Let us start. So, this was the last slide we looked at yesterday. And before we move on, any questions about previous lectures? No questions. All is clear. Okay, then let us go on. So we are still in the sample preparation part, and it turns out that there are quite some uncertainty sources related to sample preparation. And now the next one is analyte decomposition. Here, let me do a small additional explanation. There are many people who would say that, hey, wait a minute, this you should not include as uncertainty source. This should be part of validation, method validation, where you make sure that your analyte does not decompose. And if you find that the analyte decomposes, you should change your method into such a shape that it does not decompose. This is true. Of course, analyte decomposition has to be addressed during validation and during method development. And you have to make all the efforts possible that your analyte does not decompose, like using lower temperature. There are auto samplers with cooling that are nowadays available. Also, sample preparation manipulations can be done at reduced temperature. Sometimes it is important to do some manipulations under inert gas atmosphere so that the oxidation does not take place. But even with all that care, you might still end up with a situation that it almost does not decompose, but slightly, a little bit, it still might. Also, almost inevitably, your validation will be only partial in the sense that it is rarely possible to encompass all possible matrices and all possible situations in validation. We will come to that later on when we will discuss validation. So that in routine use, you might encounter situations which do not exactly match with what you encountered during validation. And therefore, you also might have some effects or the same effects, but to different magnitude compared to what you had during. And if I take this soil as an example, why is it really difficult to validate methods that have soil as matrix? Is that soils are incredibly diverse. So many different types of soils. Soil can be sandy kind of soil, which is in like desert areas and places, but then it can be very organic rich, which here in Estonia we find in wetlands and bogs. And then it can be very clay rich, which again is completely different kind of matrix. And in this small country, Estonia, only 45,000 square kilometers. Some of you may laugh at this area if you think, how big is your own country? Some of you come from countries which are tens of times bigger than our country. Even this small country here has roughly 20 different soil types, which act as different matrices in terms of analytical chemistry. You can imagine then, especially if we take some, let's say, really diverse countries such as Peru maybe or Brazil, etc., how many different types of ecosystems, biosystems, and therefore how many different types of soils you have in those places. So that, okay, you do soil analysis, you validate for some soils. Maybe here in Estonia, we managed to validate for maybe 12 types of soils, but then come some other types which are still not within that validation. And your analytes might behave somewhat differently. And now if I come now back to this slide, this is just one example. Decomposition also might depend on delicate nuances of matrix of the real sample, etc., which you might not foresee. So that with analytes that then tend to decompose, this often needs to be additionally accounted for in uncertainty. And again, interestingly, the Nordtest approach, which I've been mentioning here already a few times, that approach actually does that automatically without additional effort from you. We will come to that later, and I will show how that happens. In the ISO-GAM approach, the modeling approach, you have to take it into account, like yourself, you have to determine how big the effect might be. And then, okay. Now, analyte decomposition is problematic to a very different extent depending on what your analyte is. And of course, the best situation is if you analyze this element, because elements really do not decompose. We leave here aside all kinds of radioactive things, which is, it's rare. It does not really happen. So if it is cadmium determination in whatever the matrix, you can be sure that that cadmium atom or cadmium ion does not fall apart into different. It might do other nasty things, which we will come to in the next slides, but decomposition is not among them. Now, if we think about simple ions, then many simple ions are really very durable, such as sulfate, chloride, etc. Nothing really much happens to them. So you can rule out decomposition almost entirely. But here is a selection of ions which are very important. These are very important analytes in different situations. So nitrate, nitrite, and ammonium all can decompose. Nitrate and nitrite are like, nitrate is an oxidizer, although it's a very mild oxidizer under neutral conditions. But still, if there's a strong reducing agent somewhere, it might be reduced. Nitrite, there, in contrast, is a reducing agent, which can be easily oxidized to nitrate. So if there's some oxidizer, like oxygen, might decompose. Nitrite is also reactive in other ways, so it's not just oxidation. And ammonium, it does not really oxidize per se so easily. Ammonium is not easy to oxidize. Perhaps I even should remove the word oxidation. It can be oxidized with very drastic conditions. But microbes can take it and convert it into something else. Then it's not ammonium anymore. So you can lose it by microbial action. Then there are many organic compounds which are quite durable, simple aromatics, etc. They don't really decompose. Yeah? So, for example, if you do, which is an important type of analysis, volatile organic compounds, VOCs as they are sometimes called. Volatile organic compounds are a big topic whenever you have some, let's say, laminated surface, plastic, also some paints, pore coverings, etc. Many of those things are produced using solvents, and some solvent residues remain inside. And you all probably know that if a new house is built, everything is new, and when you enter it, it smells with all kinds of chemistry. This is because all the materials are new. They all have some solvents, and all those solvents come out. Yeah? With time, all that disappears because most of the solvent just evaporates out, and the ventilation takes it away, and it goes away. But initially, it is there. And there are some solvents which are forbidden under some conditions, and so on and so forth. So determining such volatile organic compounds is important. Among them are, for example, toluenes, all three isomers of silenes, ethyl acetate, acetone, also benzene. Yeah. All these compounds that I just mentioned, under normal conditions, they don't really decompose. And decomposition in such analysis is not really an issue. But they are all volatile, which will be one of the next slides. whereby they are nasty by some other means. But then, of course, there are numerous organic compounds which are very reactive. Many of them are quite strong reducing agents. And if you're not careful, or if it's simply that you are working on and under ambient conditions, air can access your solutions, then air can partially oxidize those. Ascorbic acid here is a very good example. Ascorbic acid oxidizes very easily, but just air is usually not enough. But if there are certain metal ions also present there, they catalyze this oxidation very much. So that, again, depending on nuances of matrix, ascorbic acid losses can be very different. Yeah? If you validate it with one type of matrix, but now you're analyzing slightly different, then you still might have losses. And then finally, what is very big topic and huge variety of compounds, all kinds of metabolites, bioactive compounds in biomolecular, biomedical analysis, myriad of all kinds of compounds. Some of them are quite durable, but some of them might be very reactive and really prone to decomposition. So depending on what you have as your analyte, you at least should think about the possibility that the analyte might partially decompose. And of course, then again, you should do whatever you realistically can to minimize the extent of decomposition. Now, what is also very important is this example. Let us examine this example now. Really, really important thing. Perhaps I even should possibly even make this thing into a separate slide, because it explains that whenever you have a decomposing analyte, then of course it depends on the real exact situation, but usually you are more in trouble at low levels. So suppose you have some kind of system where there are microbes, and suppose the concentration of microbes or the number of microbes is sort of constant. And suppose the microbes are able to eat 66 molecules, or sorry, 60. Oh, interesting. I have here actually should be 40. Right. So they can eat some number of molecules, and if now you have 100,000 molecules and they eat 60 of them, you still have 99,940 molecules remaining, which means that the loss is 0.06%, which for almost all chemical analysis is negligible. The loss is so small that usually it's far below the uncertainty range. As we discussed last time, the most accurate chemical analysis typically has uncertainties 1%, 2% relative or something. And here we have below 0.1%. So it's probably insignificant. But if on the other hand, you have only 100 molecules, you have trace levels, then you lose 60% of your analyte, meaning you get your result wrong by more than 2 times. These numbers are just thought out numbers. Of course, you probably all understand that even 100,000 molecules is ultra trace. It is extremely small number, not to speak of 100. So usually it's myriads of more molecules in your samples that you determine. But it's simply easier for me to bring examples with these numbers. Otherwise, the number of zeros is so big and it's not so easy. But you can multiply yourself by a few billions. You get something more realistic. I will also correct. Please raise your hand who understood this example. Good. People on the internet. Carlos, Sarah, Haider. Good. And let me also stress that this kind of example is not unique to decomposition. There are a number of effects, which also some of will come on next slides, where the same holds. Some reason for losses acts as a, not exactly, of course, constant, but more or less constant fashion. So that if you are running analysis of main components, completely unimportant, negligible, you don't have to think about it. But if you're running trace analysis, it becomes extremely many things like that. So that the bottom line, it's really important to know the properties of your analyte. And whenever you do something that already has been done by others, of course, read carefully what is written and read the standards or publications or documents, or whatever it is that you get, and see whether people have brought out those. Okay. Now, next thing is derivatization reagent or derivatization reaction. By the term derivatization reaction, I use it here in very, very broad sense. It embraces also, for example, the photometric determination of nitrate, phosphate, etc. Yeah, with phosphor-molybdenic reagent, for example. Then derivatization often times is done in liquid chromatography, yeah, for example, for achieving retention or for better mass spectrometric properties. But also very often in gas chromatography to increase volatility and to remove, for example, carboxylic groups, which are very sticky and very bad peak shape, even if the compounds themselves are reasonably volatile. So in all those cases, your analyte reacts with something, is converted into something else, and that something else is then determined. Numerous different ways. And now, derivatization reactions have a number of requirements. So by far, not any reaction is not suitable for derivation. Number of requirements that derivatization reaction must. And usually those derivatization reactions, which are well known and used a lot, they meet all those requirements, but every now and then, again, depending on your matrix, depending on the situation, the derivatization reaction might not go exactly as you like, or might have some problems. But now, again, I have covered part of this. Let us now jointly try to figure out what are the requirements for derivatization reaction. So, please.
First thing I think about is that in the end we should get 100% the reaction go.
Yeah, 100% yield. This is often a thing that is mentioned as the first thing. Of course, correct. Anything else? Here we come again to the same point I made at last lecture with recoveries. And I said that, okay, yeah, why should we worry about 50% recovery? Let us just correct, yeah, multiply everything by 2. But whenever the yield or recovery or anything like that is lower than 100%, it almost always means that it's not constant. Sometimes you have 85, then you have 72, then you have 96, and so on and so forth. And so you have a lot of variability. So that typically derivatization reactions are not considered acceptable if they are below 100. And again, 100% means that during validation, you get 100%. In real usage, depending again what is going on with your real method, you might actually get less. But let's say the formal requirement is 100. Or let's put it very close to 100. Some tiny small amount of like side reaction, of course, can happen. Like again, if it's below 0.1%, it's almost insignificant. But it's actually below 0.1%, it's fully insignificant. Okay, but there are other things that are important. Yeah, Hamdi? Yeah, yield a stable derivative. And this is a tricky thing because there are many derivatization reactions that actually do not yield very stable derivatives. This nitrite determination is a very good example. It is determined with some photometric reagent, typically photometrically, but that color that it develops is not stable. So that, although we write here, yes, stable derivative, even nitrite standard method acknowledges that color is not stable, and it is written there that you have to measure within some time frame. Yeah, but we've done here some investigations and found that even within that time frame, it's not necessarily stable. So that again, these are, let's say, like fundamental requirements, but real life oftentimes not as good. Yeah. Okay. Anything else? Yes, let's say, let's put it, improved detectability or improved suitability for the method. Otherwise, there's no point to do any derivatization. Always is extra effort, always brings in additional uncertainty sources, yeah? Makes analysis always more expensive. And if you don't have any gain, there's no point to do that. Yeah? So the derivative is better suited for the analytical technique that you are using than the original. Anything else? Yeah, could you take some microphone, like throw the cubic? Yeah.
That it doesn't create byproducts that could interfere.
Indeed, to some extent, 100% yield already tells you that no byproduct, because otherwise you don't get the 100% yield. But what you say is still very very reasonable. And let's put it this way: one product per analyte. And let me explain what that means. You see, you might have 100% yield in the sense that all your analyte reacts, but maybe depending on conditions, several different molecules can form. That is bad, because what that means is that eventually in your chromatogram or whatever you do, you don't have one analyte peak, but you have maybe 3 or 4, which is nuisance, because now you have to integrate all those peaks. You have to make sure that they don't overlap with anything else, etc. So typically it is required that the reaction proceeds uniformly and only gives you one. For example, let me just bring in such an example that, okay, amines. Amino group is oftentimes derivatized. It has different reasons, which I'm not going to explain in detail, but is often derivatized. And now there are many polyamines available, yeah? Diamines. Now, if it is a diamine, then what you want is either that both amino groups react so that you get diderivatized, fine, that's okay. Or only one reacts. What you don't want is a situation where in one case one reacted, in the other case the other group reacted, and the third one is that both reacted. If it's now unsymmetrical amine, so the amino groups are not equivalent, this gives you 3 different derivatives, and in your chromatogram you're then going to have 3 different peaks, which is a headache, yeah, which you don't really want. Was it understandable that I explained? Okay. Haider is saying derivatized product doesn't react with other components. Haider, this is pretty much covered by stable derivative. So stable means that it's not reactive, doesn't react. Okay, but there's still something. You have covered the most important things, but there are still something. Let's put here. Oh, sorry. Oh. Yeah. You have covered most, but there's still something remaining. Yes, let's put it, yeah, cheap, yeah, convenient, you know. Perhaps easy to use. Yeah, these are like things that we always want, yeah. Okay, but there's still something that is important. Very good. This is indeed one which I was hoping to hear. So usually not usually, but always derivatization reagent is added in excess, and mostly in large excess, sometimes in massive excess. You might have it 10s, maybe even 100 times more than the amount of analyte that you have in the sample, which also might contribute to 100% yield. You know, sometimes if you add, first of all, you don't know how much analyte you have before you haven't done the analysis. You need to add more anyhow. But it sometimes can be that if you add in high excess, then you also will have with higher probability this 100% yield. And this means that after derivatization, the reaction cell, or let's say your solution, always has excess of derivatization reagent, which might still be in the original form of the reagent, or it might have decomposed or reacted with something else or whatever. And also one reason, by the way, why oftentimes high excess of derivatization reagent is added is that often in your sample there are other things that are not your analyte, but might react with the derivatization reagent. So that if you add just enough for the analyte, actually other compounds might consume it. So that there's one of 2 possibilities that is needed. Either the excess does not interfere, or the excess is easy to remove. One of these 2 is necessary. Okay, yeah. Now, there is still something that you haven't yet mentioned. Yeah. Perhaps let me put here also safe. So I'm putting all these cheap, convenient, easy, etc., all as one thing, which are simply like the usual thing that we want of the chemistry. Safe means that preferably it should not have some highly toxic reagents or highly toxic things there. There's one more, like how would I put it, like chemically important thing, which is not related to cost or safety or such things.
Something, but not sure. It's not like applicable in the cases selective.
Yeah, this is selectivity is a very interesting thing. Let's put, let's see how we word it. Let's put it suitable selectivity. Yeah, this is a good point. Sometimes you would like that the reagent would just derivatize your analyte, yeah, and only one. But sometimes you would like that it would rather be universal. For example, derivatize all amino groups or all amino compounds that are in the sample. This is why I'm writing suitable. So sometimes you want it to be really very selective. Sometimes you're not so interested in selective. So this can be very different. But of course, for example, if you do nitrite determination, then you need that the photometric reagent really is selective to nitrite only and does not react with other. But there's still one chemical thing which nobody has yet mentioned. Yeah, please. Yeah.
I don't know, like maybe soft conditions like that can have an impact in our method or something, like the soft conditions, or maybe like talking about the reaction, like to be as fast as possible.
Yes, you said it in a very sophisticated way, but essentially what I think we're saying should be reasonably fast. Yeah. Exactly. This is exactly the, let's say, the last thing that I was hoping to hear. Derivatization reactions don't need to be instantaneous. Usually they don't work like this, that, okay, as soon as you mix and shake, oh, now it's already reacted. Oftentimes they take minutes, maybe even a couple of hours, but that can be managed. These days, quite often what is done is that derivatization is carried out in autosampler, so that people don't really do that like themselves, but autosampler manipulates those things, and then what you always can do is the autosampler does the derivatization, and then it simply has some time lag, maybe waits for 1 hour before it starts injecting. Autosamplers are becoming increasingly powerful and almost like small lab robots. And then there are, of course, nowadays like separate lab robots also. Autosamplers nowadays do dilutions and things and all kinds of things that you might wish. Not all derivatizations, of course, can be carried out in autosamplers. Sometimes there are more manipulations needed, but sometimes it is. So that just, let's say, usually if it is something like tens of minutes that are required for the reaction to be completed, then that's usually fine. Perhaps we put here that preferably it should work at ambient temperature. It is also possible that everything is like all the samples are heated to boiling temperature for carrying out the reaction. That is something that people don't really like at all, yeah. Okay. Wow, yeah, that's good. Okay, very good. And now, if we now come back to where we started from, we are still in the middle of uncertainty sources, then you might, of course, expect that whenever you have a derivatization step, something else might react with the reagent, recovery of below 100%. As I said, not always the derivatives are fully stable. Also, there might be interference from the excess of the reagent, or there might be interference from other components of the sample that were derivatized. So all kinds of things can come in. So whenever you have derivatization as part of your method, you should at least think of possible problems that derivatization. So, yeah, please, yes. Could you send the microphone?
I just want to add, if for obvious, is it also the same under the principles of accessory agent, easy to remove, easy to sort of deactivate it or to quench it?
Yeah, doesn't it, or easy to remove? Let's put it quench. That means the same thing. Yeah, Maitane? You have to take them into account in the sense that you have to think about them. It does not necessarily mean that in your case they cause any uncertainty. So, as you see, I'm giving you these uncertainty sources as a very broad picture. First of all, in many cases, you simply don't have any derivatization. Then obviously, you cannot have that as an uncertainty source. But also analyte decomposition. If it's lead or cadmium or sodium or potassium, they do not decompose. You don't have that uncertainty. Also, sometimes you might have an analyte that possibly can decompose, but you might find out that, yeah, well, under our conditions, it really decomposes so little that you don't really need to take it. So it is first of all, you need to be aware that such possibilities exist. And in every separate case, you have to discover whether it is important for your case or not. Did I answer? Okay. Now, next thing, contamination. Contamination means that analyte comes into your sample from somewhere, so that you end up with having more analyte in your sample than there was originally. Yeah. If you see most of these, let me ask you. Yeah, let me ask you this question. How is possible contamination as an uncertainty source different from what we had previously? Decomposition, we had insufficient extraction efficiency. We will have in one of the next slides, we have volatilization, that part of it evaporates. How is contamination different from those? Elliot?
One, I guess that contamination rises our analyte levels.
Exactly. Most of these, let's say, sample preparation uncertainty sources, especially at trace level, in most cases you lose some analyte, it goes away. But contamination works the other way around. Yeah, it gives you more. There's one more uncertainty source that we will come later on, which also tends to increase your results. So that you see some uncertainty sources push it one way, some uncertainty sources can push it another way. Now, contamination obviously comes. Oh, wait a minute. I want this. So, contamination, of course, usually, first of all, I would say it is not really an issue if you determine macro components. It comes into play if you determine low levels of something. So, for example, if you do some food analysis and you're determining some, I don't know, let's put it, protein content in wheat or fat content in cheese, the contamination, not really. Maybe a few percent or few 10% of analyte by mass in your sample, then contamination usually. Contamination comes into play at trace level. If it's few percent, tens of percent, and usually also if it's 0 point something percent by mass, usually contamination is not. It really comes into play at really very low levels. And secondly, it typically happens when the analyte is reasonably widespread. So that, for example, if you analyze some very sophisticated, strange molecule, yeah, which is very rare, yeah, then it's not really expected it is flying in the air and jumping into your vessel, or that you breathe it out or something, yeah. So that usually it's widespread analytes, which I have some examples here. And let's now see which are the analytes and situations where you really need to be aware of contamination problems. So first of all, if you do work with elements, I have written here widespread elements, but that actually also can concern less widespread elements also, such as maybe lead or maybe copper, etc. It depends on what is the level in your samples. If it's really ultra traces, then many elements can have problems here. For example, here is one example: purity of semiconductor materials, ultra pure chemicals. But it also can be, for example, seawater. For example, trace elements in seawater are at very low levels. In seawater, you of course have a lot. I mean, especially ocean water, not near the coast. Yeah. But let's say in the middle of the ocean, there's very little, especially very little dissolved trace elements. So that all kinds of contamination becomes an issue with almost all the elements, except of course sodium and potassium and magnesium, which seawater is full of those. Yeah. And what do you do? First of all, with these elements, at least that I've listed here, you do not use any glassware. And those of you who took the atomic spectroscopy course last semester, you have already got some information and some guidance on that. And in fact, at ultra trace level element analysis, people typically use plastics, so that the solutions do not get into contact with glass at all. For all kinds of elements are inside glass. Might not think that they are very widespread, but if levels go sufficiently low, glass can leach out all kinds of elements. And then secondly, of course, if it's really serious, you work in clean rooms. Which are rooms where all the air enters only through higher level filtration. You put on some things, yeah, you either change your clothes or put on special clothing so that you are all covered, and then you walk into that room and do the manipulations there. Also, it can be done in some glove boxes, so that the box is all closed and you go inside just with gloves and you do the manipulations inside there, and then you also don't contact. The next analyte, which is everywhere, is water. In many cases, water, of course, is our solvent for all kinds of analytical work, but water is also a very important analyte. So in all kinds of industrial chemicals, plant oils, fuels, etc., water content is a very important parameter in all of those, you know, for trade and for determining the price of the material and so on. Also, water is important in cereals, for example, in grains. Their water content also determines can they be stored for a long time or not. Water determination is a very big thing. Yeah. Obviously, as you know, water is everywhere, and every breath that you breathe out, there's a huge amount of water vapor that comes coming out of you. So that human being is a very contaminating thing, yeah, in terms of water. And although I have put here high purity materials and or solvents and dry materials, actually refers to many more objects if water content is low. I would say water is nasty to the extent that even if water content is not very low, so it's not really ultra trace analysis, still ambient water can be a big headache. And then what people do, usually water determination is done with special equipment which is totally closed. You may know that there is a type of titration called Karl Fischer titration that is used for water determination. And in Karl Fischer titration, you never work the same way as with normal titration. You don't take and now you pour your titrant. You never do like that. Your titrant is never in contact with air. Everything is closed. You typically use special Karl Fischer titrator, which only has tubings and small pump and so on, which pumps liquids from here and there and so on. And then there's, of course, the coulonometric Karl Fischer titration, which does not use titrant as such, but iodine, which is an important reagent there, is generated electrochemically. And the integral of current over time determines how much iodine was consumed, meaning how much water was in it. And that is also, everything is closed, completely closed. Humankind has developed water determination very well, actually. So that there are nowadays available very good ways to determine water content, even at very low levels. So if you really want ultra low level water, then you have to place all this titration equipment inside the glove box, which has inert gas in it, so that there's almost no water coming in from. Then the next thing is, of course, air components. Water is also air component, but now the other air components, oxygen and CO2, again, they are everywhere among us. Most of you right now in this room have done quite recently oxygen determination, so you've seen the art. But of course, you in winter school, the way you did that, you actually made use of the thing that oxygen is everywhere among us. So you essentially calibrated your meters in a solution, which, okay, there was two ways. Either it is saturated with air and you simply use saturation values from like tables, or might be you might use special Winkler titration values. And as soon as your meter, your electrochemical oxygen meter, is calibrated, then ambient oxygen is no problem for you anymore if you measure in systems which themselves are at equilibrium with oxygen, with air. So you went to the lake, yeah, and did measurements there, and you did not really worry about the fact that air is full of oxygen, because that air is in constant contact with water, and that is how it's supposed to be. So you were not trying to measure oxygen, for example, in some water sample where there's almost no oxygen inside. That would have been a completely different thing. But I don't know how much you noticed when IRIA did this Winkler titration for the reference value. That was a very tricky, numerous different manipulations, of which some were necessary to do with really careful avoidance of ambient air. She had her own tricks for doing all that. For example, when she brought the samples back from the lake, you may have noticed that she did not have them just like that. Those sample vessels were inside water, inside the same water that she took from the same lake, to avoid that atmospheric oxygen would distort the amount of oxygen. So that like the vessel was submerged into water, where the water composition was essentially the same as inside the vessel. So this is how it is. But in any case, yeah, again, why I'm explaining all these things, you have to think about these things when you do that kind of analysis. When you go to your future job somewhere and they do something like that, you have to ask questions. Okay, yeah, we do this, interesting, yeah, but the analyte is everywhere. How do we avoid that the analyte everywhere influences our measurement? Then people have to explain you. Okay, high purity gases, high purity water. Here can be very important. In high purity gases, we usually really don't want oxygen and CO2 also. In high purity water, oxygen usually is not determined at all, but CO2 is, because CO2 causes increased electrical conductivity. Yeah? So CO2 a little bit dissociates, is converted in water into carbonic acid, and a little bit dissociates, creates ions. So that highly pure water has to be essentially devoid of CO2. And again, people use special equipment, and very often people use online measurement. So again, those of you who go to Lyon, you might, depending on what your thesis topic will be, you might end up working with some of such systems where the analysis is done directly inside some process in online or in inline. And then finally, all kinds of compounds that living organisms produce. So you as a living organism, of course, when you breathe out, your breath has a lot of water vapor, CO2, but besides also other things. Different amines, some little level of acetone, and other compounds that you are breathing out constantly, which is very small levels, very low levels, most of them. Under ordinary conditions, they don't really influence, but in some cases, they can be really dangerous. This becomes important in all kinds of biomedical or biomolecular work. And what people typically use for avoiding contamination from humans is something called laminar flow hood. Do you know what a laminar flow hood is? Some of you know, some of you don't. Okay. Laminar flow hood is a... Sorry? Yeah, exactly. It is a standard tool for biochemical labs. And it is like an inverse of the fume hood. What fume hood does, it sucks air out to protect you from chemistry that is going on. Laminar flow hood does exactly the opposite. The back wall usually is fitted with some kind of fritted material with very efficient filtration system, and air flows from that back wall against you, and whatever you breathe out is blown behind your back. So that flow comes against you, and fume hood protects you from chemistry. Laminar flow hood protects chemistry from you. Yeah, so that whatever you breathe out or whatever you do, yeah, it all goes behind you. And as I said, yes, it is like a standard tool, like in many kind, like in synthetic chemistry, fume hood is a standard thing always used. And for biochemistry labs, laminar flow hood is a standard thing. It is, besides analysis, it is even more important for all kinds of bacterial culture growth, and etc. Because sometimes it can happen that some tiny small thing that evaporates from you will make the growth different, or will kill all the organisms, or whatever. That can be, it can be very small amounts of compounds can have very big effect on microorganisms. Very, very tricky and typically not very well. So, any questions? Okay, but now I have here two questions for you. First of all, we haven't discussed this at all. It will come later on to some extent, but let me already ask now. How would you detect contamination? What would you do? You want to be sure that you don't have contamination. Did you? Yeah.
Like when you're carrying out any reaction, we can just take in between, check the like check some product or check whether there is contamination or not.
I did not understand.
Like when the chemical reaction is carried out and the product is formed, we can just check the product whether it is contaminated, or in between the process we can check some amount and like whether there is contamination or not.
I would say mostly people, I'm not fully sure I understood correctly, but I think mostly people would not do it like that.
Okay.
But let's see, Maitane, you were the next guy.
Our cell technique carried out with our sample.
Exactly, yeah. So blanks are standard way of determining contamination. There are different kinds of blanks, of course. And then it's also more tricky, but the best way of, or the best kind of blank for this is if you can get a matrix which is essentially the same as what you are analyzing, which simply does not contain your analyte. This can sometimes be very tricky because you must be really sure that this analyte is not there. Sometimes it can be done. For example, suppose it's some kind of drug research, yeah, and there are some patients who are administered some drug, yeah, and blood is analyzed. And now and this is a new drug, yeah, not yet on sale, yeah, first time tested. Then your blank matrix could be blood from some other people who've never seen or never really experienced that drug, and that would be almost surely not contaminated with that drug if the drug is completely new. Yeah, nobody has had it. But then sometimes, yeah, it can be tricky to get. But then even what also might be of some use is simply a blank, like let's put it
reagent blank, so that you don't put any sample at all, but you add all the reagents, you do all the derivatization manipulations. Let's say, you take, instead of your sample, you simply take ultra pure water, and then you take all the manipulations, yeah, and now you put the sample into the machine, and if now you still see the peak of your analyte, and if you can sure that this is your analyte, then obviously during that manipulation, somehow. But now, yeah, okay, this is the standard thing that people do, and then the very important part of validation. So method validation involves that kind of thing. Yeah, Gleb?
I was wondering if you could use reference standards for the same thing, or is it just more expensive to do?
You can, yes. If that reference standard, if you are sure and you know that there is this compound inside, then yes, you can. But oftentimes what happens is that if you buy a certified reference material, okay, suppose it's trace elements, and suppose you want to analyze traces of something that's not commonly done, let's say niobium, yeah, okay, you want to analyze trace niobium in some kind of thing, in soil maybe, yeah, and now you buy a certified reference material, and you say, okay, lead, cadmium, copper, nickel, oh, no niobium listed, very good. But that does not give you any guarantee that there's zero niobium there. They simply did not determine it. So you might be in difficulties finding certified reference material which explicitly tells you that this thing is missing. You see what I mean? They usually certify the certified reference for some analytes that are present, but don't certify for elements that are not there. Yeah?
Why can't you use a reference standard which has the analyte, and if you just detect more than it's given, then you know it's contaminated?
You can, yes. This is fully possible. But very often what happens is that there might be also other reasons why you get more. Like simply, let's put it simply, variability of the method. In principle, you are right. So for example, if you get 3 times more, you buy some reference material, there's some ultra low level, and now you do the analysis, you get 3 times higher result. And almost surely you have some real problem. But if you have it higher by, let's say, 15% at ultra-trace analysis level, you cannot say that it is surely contamination. It can be also something else. But in principle, you're right. Yes, you can. Anybody else? Any comment? Okay, if not, then I have another one for you. Yeah, it's here. I said that contamination typically is an issue with analyte, which is very common. But can it also be an issue with a rare analyte? For example, something that is not universally everywhere here. And if yes, then how can it happen? Suppose it's the same thing as new drug, yeah, new developed drug, nobody using, yeah. Your lab is the only place you have. Yeah, Hamdi, I think you were the first.
I'd say yes, and the contamination might happen from the sample itself. So, like, if I took a subsample and I want to analyze this subsample, maybe the transfer from another subsample that I'm not analyzing right now might make contamination.
So you have different samples of the same, and some sample has higher level, and that sample contaminates your lower. It is possible, but I would say it's not the main cause usually.
That in the have a per analyte, there might be more common way analyte and they cause contamination. Analyte is rare, but contaminant, but similar.
You are right, and that can happen, but this we will qualify as interference, insufficient selectivity, and that will come later. We'll have a separate discussion on selectivity issues, which are very important and big issues, but this is not considered contamination. If there's something else which behaves similarly, we don't speak of it as contamination. Yeah, with the same. Somebody else had hand up. Was it you, Christian? No? There is a very concrete reason how. Yeah, Hans. Could you give? You're
using the same tabware, the same analyte from a previous batch run.
Okay, you are very close. Let's take that. This is the thing. So. Usually what happens is, okay, yeah, new drug is developed, yeah, here are blood samples, yeah, I need to. But you almost always also have this drug in pure form so that you can prepare calibration solutions. And for preparing calibration solutions, you first must weigh this 100% hugely concentrated material. Okay, then you make some stock solution, which still might be cosmically high concentration compared to any of your blood samples. Now you do solutions, and now you make your standard solutions. You use lots of glassware for that. Now some of that glassware gets used for sample preparation, for diluting your sample or some sample work. Then you can easily contaminate in such an extent that in your sample solution, the concentration might get several times higher than it originally was. For avoiding that, what ultra-trace labs often do, and which is a very reasonable thing, they have completely separate rooms. One is for samples, and they never bring any pure substances, any calibration solutions, any glassware from the other lab, and the other lab is only for calibration. Volumetric work, glassware, all is there only for calibration, and here it's only for sample preparation. And they never mix that glassware or other labware between them. This might be really important. Ultra-trace work. Because some analytes have the very nasty tendency to absorb on the walls of vessels. Might be difficult to get them away from there. Absorption, by the way, will come in one of the slides soon, yeah. And then it might be desorbed exactly at the most inconvenient moment when you preparing the sample for the ultra low level sample where the ultra low level of analyte is inside. So cross-contamination between samples, and especially between samples and calibrants, is a big thing. Okay. If no questions, comments. Haider says, from the contaminated glassware. Haider, I think you might have meant the same thing as what Hans said and what I just explained. Yeah, that you contaminate your own glassware with the standard substance, and then you contaminate your. Yeah, okay, yes. Cool. Now, two more things: volatilization of the analyte and adsorption of analyte on walls of vessels. Volatilization, of course, is problematic typically with volatile compounds. It's volatile organic compounds, very good example of that. Example, sampling such plastics where you want to determine how much of the volatile compounds is inside is a whole tricky thing because they lose those compounds constantly. And usually people use some standard methods which are standardized so that everybody would do exactly the same way, so that the results would be comparable, and so that the results would also be comparable to legislation, because the legislation oftentimes prescribes how much volatile organic compounds is allowed. For example, if you build a kindergarten, yeah, then all the materials must be with very low volatile organic compounds, because for kindergartens and for schools, for example, also for hospitals, there are different rules than for maybe shopping centers. The thing is not so. Also, some elements can be volatile at some conditions. For example, under acidic conditions, you might easily lose selenium, you might lose boron. And for example, in dry ashing, if you don't do wet ashing with acids, but you simply do dry ashing, simply heat your samples, and for example, some plant material, you simply heat at high temperature in muffle furnace, you might lose part of zinc and iron. So might get volatile under such conditions. So wet ashing actually is better than dry ashing for most elements. And of course, this is again especially problematic with trace analysis. And now adsorption can also happen with different analytes. But if we speak about elements, then notorious and very famous for all kinds of adsorption problems is mercury. So determination of traces of mercury is a whole science in itself. It is a very nasty element for many ways, including that mercury typically has the lowest permissible limits in almost anything that you can think of. Meaning your LODs for mercury must be lower than your LODs for almost any other element. Of course, means that you are almost always running ultra-trace analysis. And then, on the other hand, mercury is terrible for volatilization, as you might expect. I did not mention it here, but mercury should be here with big black letters, yeah, in this list also. And it is phenomenally able to adsorb on walls of. So these things also you should take into account in sample preparation. So now we have finished with sample preparation. You see, you can think how long we have worked. Actually, we started last time and already discussed last time, and now most of our today's lecture, we have only now discussed still sample preparation, which gives you some idea how big issue is sample preparation in analytical chemistry. But now let us move on to volumetric operations. So typically volumetric glassware these days is quite accurate. If I'm saying here oftentimes uncertainties that, okay, relative uncertainty 1%, 2%, 5%, 10%, then glassware is much more accurate.
So for example, something like 50 milliliters volumetric flask or 10 milliliter volumetric pipette, they have uncertainties clearly below 1%. If you overestimate. But volumetric operations still can cause important uncertainty contributions in at least 3 cases. I'm not saying that these 3 is exhaustive list, but these 3 cases certainly are those. First of all, if you do really high accuracy work, such as, for example, preparing some very high accuracy standard solution, which many people afterwards will use, then you have to be very careful also with volumetric. Then, and this might be the most important reason or most important case nowadays, volumetry with very small volumes. This is very interesting how analytical chemistry has changed over time. When I was a student, the standard volumetric flask that we most use was 100 milliliters. The most common volume to pipette was 10 milliliters. If you now go to analytical labs, then I think most volumetric flasks are maybe 25, maybe 10 milliliters, and there are volumetric flasks below 10 milliliters. And most pipetting nowadays, of course, is done with these automatic pipettes. Oftentimes, the volume that people pipette is 1 milliliter or 0.5 or 2 or something. So that the volumes in analytical chemistry have contracted by roughly an order of magnitude in that time. So that more and more and more people work with very small volumes. For example, usually nowadays when we do calibration graphs, we don't do 7 times 100 milliliters of solutions. Usually those solutions are maybe 7 solutions of 10 milliliters each, yeah? And oftentimes they are prepared by weighing so that a lot less solvent is used, a lot less standard substance is used, a lot smaller amounts of acids and bases and reagents, everything is used. And this, of course, for good reasons. First of all those things cost money, but also waste disposal nowadays costs much more than it used to in the past. Yeah? So once you have finished your analysis, when you have all those hundreds of milliliters of liters of solutions, which you are not allowed to throw into the sink, you have to utilize them, send them to the company which takes care of them, but the company, of course, wants money for it. Yeah? People try to work with smaller and smaller volumes. And by small volumes, I mean few microliters to few hundreds of microliters. 1,000 microliters obviously is 1 milliliter. So let's say it's around milliliter and less, or let's say milliliter and slightly more and slightly less, and then of course also a lot less. Yeah, for example, pipetting 10 microliters, which is 0.01 milliliter, nowadays is not rare. People do that kind of pipetting. And in all those situations, uncertainty of volumetric operations can be substantial. Usually, if you do pipetting of 10 microliters, the uncertainty is pretty big. I would say several percent. But people use that kind of thing mostly in cases when that volume is either not critical or the overall analysis uncertainty so quite big, yeah, maybe 10 plus minus 10%, then you can afford bringing in additional uncertainty with volumetric. Now, usually when you manipulate small volumes, you would rather use automatic pipettes, not glass pipettes. So pipetting with a glass pipette 10 microliters, I'm not sure it's a good idea. Very small. And also there's a thing that is actually very useful, not so much used but in analytical labs, but we use it quite a bit in our work. There are precision syringes. For example, 100 microliter precision syringe. If you need to dispense something like, let's say, 50 microliters, then that syringe is a very good thing.
because syringe very nicely holds liquid inside, does not go anywhere. There's no any question that some droplets remain somewhere on the wall, or all those kinds of things go away. And then, of course, oftentimes when you work with such small amounts and want high accuracy, it oftentimes might be more reasonable to weigh, not measure volume, but measure mass. In our group, again, depending on what work we do, we oftentimes do such, let's say, important and critical solution by mass, not by volume. And now the last thing, which is extremely nasty, is if you need to measure accurate volumes of volatile compounds. For example, if you need to pipette acetone or diethyl ether. Diethyl ether actually is so bad that I don't think you actually can pipette it in any reasonable way at all. In such cases, you should try to organize your work in such a way that either this amount that you are pipetting does not really influence your analysis, or you do all this work in some completely different way, for example, by weighing it. So that small amounts of volatile compounds is the worst combination that you can have in volumetric work. And that can bring in huge uncertainties if you don't do that. Now, if we now speak of uncertainty of volumetric operations, we also can speak of some specific kinds of uncertainty. If we say that, let's say the big overarching uncertainty source is volumetric operation, but it has in itself several specific sources of uncertainty. Let me go through them one by one. First of all, there is something called calibration uncertainty. What that means? Suppose you have this volumetric pipette, there's a mark somewhere, and this is supposed to be 10 milliliters. And now this mark, the place where this mark is placed has an uncertainty, so that even if you do perfect pipetting at perfectly 20 degrees centigrade, etc., 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 you do everything perfectly, you still don't get exactly 10.0000000 milliliters because the mark itself is not in the exactly right. It always has some uncertainty. The same is true for volumetric flasks. The same is true also for automatic pipettes. They don't have any marks, but their inner system is also calibrated, and it also has calibration uncertainty. Meaning, with the same volumetric pipette, if you pipette many times, then always you get slightly more, slightly less. Okay, there are also the, let's say, the repeatability uncertainty, so that you can, your volume also fluctuates from pipetting to pipetting, but because of that calibration uncertainty, all your volumes might also be biased, meaning on either on the low side or on. Then the next is, of course, repeatability. Repeatability is an uncertainty source which is inherent in any operation that you do. Also, sample preparation has repeatability, weighing has repeatability, peak areas have repeatability, pH meter readings, and then so on and so forth. So everything has it, which simply means that you try to pipette exactly the same way, the 10 milliliter volumes, but you slightly get different volume every time. This is just because of all kinds of tiny, small nuances, and repeatability uncertainty does not mean that you did anything wrong. No, it is inherent in all work. But of course, more skillful person has lower uncertainty and less skillful. More skillful person is able to do operations more like uniform. So here is again like another answer to, I think, Gleb, you brought this up last time, that from which point we speak of a blunder and from until which point it's still like normal. Here is it, yeah. You can pipette with very good repeatability or slightly worse repeatability, but this does not mean that you do anything actively wrong. The next thing is tricky to understand, but it actually is not a very difficult concept, and it is about temperature. So it's the temperature effect, uncertainty due to temperature effect. Here I need to explain first of all the following, that all the volumetric wear, essentially all the volumetric wear that you come across in a laboratory is calibrated at 20 degrees centigrade. So 20 degrees centigrade is called like the standard or normal temperature for all volumetric operations. Except if you want to do something really very extraordinary or strange, all volumetry is like, all volumetry refers to volumes at 20 degrees centigrade. Okay, now, suppose now that your room is at 16 degrees centigrade. Liquid is also at 16 degrees centigrade. What that means? Means that if you now take your pipette and fill it with the liquid, then suppose it's water, water at 16 degrees centigrade is more dense than at 20 degrees centigrade. Meaning your pipette will contain more water molecules than it would contain at 20 degrees. Even though at 16 degrees centigrade, it's still the same volume. But the word volume in volumetric analysis refers to 20 degrees centigrade. So that if you do your pipetting at 16 degrees centigrade, or if your liquid is at 16 degrees centigrade, you actually are pipetting a bigger volume. Because if you do that pipetting, now you dispense the liquid, now my liquid is here, and now if you heat it up to 20 degrees centigrade, it will be more than 10 milliliters, a little bit more, not much. Did you get what I explained? Out of curiosity, please raise your hand who thinks that understood this logic. On the internet, people? Okay. Now, you might ask, hey, wait a minute. You are completely neglecting the fact that at lower temperature, the pipette itself also contracts. And at higher temperature, it expands. But glass has pretty low thermal expansion coefficient, so that liquids typically expand or contract by an order of magnitude more than glassware itself. So that expansion or contraction of the glass, you can neglect. You can only speak of different density of the liquid. And vice versa, if now your liquid is at 25 degrees centigrade and you pipette it into the pipette, you get less molecules than it would be at 20 degrees centigrade. So now if you dispense it, cool it to 20 degrees centigrade, you have less than 10. This is what is called temperature effect of pipetting. That you did the pipetting operation at the different temperature from the 20 degrees centigrade. It's usually not really a big issue at all in analysis, not a big uncertainty source, but still it is not so difficult to take into account. I will teach you how to calculate. I'm not going to do that today. We will do that in an example. And I will then show you how it is. Yeah. And water is a good solvent in the sense that it has very low thermal expansion coefficient. If you work with non-aqueous solutions, they have roughly 8 times, most of them, 8 times
bigger thermal expansion coefficients, so that with non-aqueous solvents, thermostating of, let's say, volumetric work might occasionally be needed if high accuracy work is done. With water, you usually don't need. Now, finally, application-specific uncertainty sources. This is very interesting part, because if you read all kinds of guideline materials, manuals, and guides, then these three things that I just explained are almost always explained, and with great care. But these application-specific things oftentimes are not mentioned at all. At the same time, they can be much more important than any of the three that I already explained. So what I mean here, suppose you have a perfect burette. You have perfect 20 degrees centigrade. Everything is perfect, and you are perfectly skillful, so that you don't have any of these uncertainty sources. This is some abstract like idea, but let's just assume. And now you are doing titration. You are watching your indicator when it changes color. But because of the nature of the indicator and the titration reaction, the indicator always changes color slightly too late. You always slightly over titrate. Meaning the volumes that you display will always be slightly higher. If you now think of it, this has nothing to do with your volumetric device at all. As I explained, your volumetric device is perfect. Question is, how do you determine when the volume is enough? Okay, yeah, titration with visual indicator, of course, is not so accurate. It's better if it's like some potentiometric, electrochemical endpointed, etc., etc., etc. But we can take a different example. So suppose you have some kind of liquid, which might be some, let's say, natural. Let's make it, maybe it's some juice or some slurry or some pulp made of some, let's say, cucumber, for example, or something like that. And now you measure its volume with a pipette, then what you easily can get this kind of thing. Let's take that this is your pipette. This is the this is the mark on the pipette. What you now might have is that the liquid is inside here, but somewhere here there's a lot of foam. And here is some pieces of something. And now here it's already like not normal liquid. Yeah, but here's foam. How do you determine where the mark now is or where the meniscus is? You have no way of doing it. Again, it might be the perfect pipette. Or pipette is actually not a good example. You don't usually pipette those things. But the volumetric flask is a very good example. Yeah, suppose you have such a pulp, you now need to dilute it by 10 times. You put it into volumetric flask and you add water. And on top of that, you will have some strange sludge so that you don't know how well you can fill. That is also uncertain. Don't know what the volume exactly is. But usually people don't speak about such uncertainty. I would say with most volumetric flasks, if you have this kind of effect, then all these uncertainty sources that I just discussed, all of them jointly are still smaller than this effect of not seeing where the right place is. Another trick or another problem that can happen with filling the volumetric flask is if your solution is very strongly colored, extremely dark. then you also don't see where the. And then, yes, in all kinds of titrations to determine where the endpoint or this equivalence point is another example, and a very common one, by the way, where again the volumetric device itself contributes not so much uncertainty compared to the fact that you don't really know at which volume now you have the equivalence, the geometric. Such application-specific sources you also should consider and, of course, try to minimize. All right, we are already 1 minute over time, so we leave the next things for the next time. Let's see. The next thing will be weighing, calibration, yeah, measurement itself. Okay, yeah. The next lecture, almost certainly, we can start uncertainty part 2. So that next Tuesday already, yeah, you can prepare also or download the other material also and have it. But today, unless you have questions, apparently not. Yeah, then we close. Thank you.